Dr. B here, and let's talk about nuclear half-life. When atoms fall apart, and I guess they all do sooner or later, though for some it might be zillions of years, they do so in what's called first-order exponential kinetics, meaning that you have a constant half-life. Every, let's say, 10 years, you'll lose half your mass. That would be if your half-life was 10 years. We can express this mathematically using this formula. Now I say formula because look, n is equal to something, so you could plug it in right here. Our variables include how much you have when you're done, how much you started with, and how many half-lives you're dealing with. So this can be used to solve for any one of those things if you have enough data. As an important tip, oftentimes problems are given with an exact number of half-lives, 1, 2, or 3. If that's the case, you don't need this formula at all probably. You can just count your way through the half-lives, remove half your stuff for each one, and come up with a solution very quickly. And I'll show you an example where we do it both ways. And here it is. Carbon-14, used to date things, has a half-life of 5,730 years. Let's say you had 10 grams to start with, but 17,190 years have gone by. How much will be left? We'll show you both the formula method and the shortcut method. Let's do the shortcut method first. If 17,190 is some exact multiple of 5,730, well then we got an exact number of half-lives, and it is. 17,190 over 5,730 equals 3. So we have 3 half-lives. After the first half-life, you'll be down to 5 grams, 2 half-lives, 2.5 grams, 3 half-lives, you'll have 1.25 grams left, and you are done. If you prefer the formula method, we'll find out what n is because we have both those pieces of data, and then we'll solve for a by directly plug in. So n is equal to, well, there it is, your 3 half-lives. So we'll put that in where n equals 3. There it is. It's 10 times an eighth. That's 1.25 grams. That's the formula method. I don't like it. I like the shortcut method. It'll only work really when you have an exact number of half-lives. But it is 3. Down to 2.5 after 2, and then 1.25 after 3, and that is your answer in either case. 1.25 grams remains. Here's 2 other problems that I'm not going to solve, but I will give you the answers to. The question here, which I'm not going to solve, but I'll give you the answer. I'm encouraging you to do it on your own and to do it both the formula way and the shortcut way. It says how much of a sample of uranium-235 were present if if 10 grams were remaining after 2.1 times 10 to the 9th years. That's like 2 billion years. The half-life is something on the order of 10 to the 8th years. What is that, 100 million years? Well, let's see if it's an exact number of half-lives. So if you divide one by the other, you might get a whole number. And if you do, use the shortcut method. I recommend you do both. If you're doing it right, you should come up with 80 grams were initially present, bringing it down to 10. This next one, we have about 0.5 gram of tritium. It's collected. And after 24 years, roughly, you're down to about 1/10 of a gram. What must be its half-life? You could solve it either way, but first thing to look for is to see if 4.456 and 0.114 indicate a whole number of half-lives. If they do, it's much easier. You should get an answer of 12.3 years. And by the way, both of these are real numbers. I looked it up, and that is the half-life of tritium. Students in my class will be asked to solve these problems to show that they watch this video and understand it. And one of them does have a question about tritium in it. This is an introduction to nuclear half-life.